An electrical falls through a distance of 1.5 cm in a uniform electric field of magnitude 2 into 10 to the power 4 Newton per Coulomb. Figure A. The direction of the field is reversed, keeping its magnitude unchanged, and proton falls through the same distance. Figure B. Compute the time of fall in each case. Contrast the situation with that of free fall under gravity. You can see in figure. Here the electric force Fe is equal to Q into capital E is equal to ma, implies that A is equal to QE upon m. Linear distance travelled at the end of the time t is d is equal to v0 t plus 1 half at square. Therefore d is equal to 1 half, keeping the value of a in bracket q capital E upon m bracket over t square, where v0 is equal to 0 and a is equal to q capital E upon m. Therefore t square is equal to 2m dqe. Therefore t is equal to under root 2md upon ee. Equation 1. For electron and proton, magnitude of the charge is q is equal to e. From equation 1, time taken by electron to fall through a distance d opposite to electric field te is equal to under root 2 med upon ee is equal to under root 2 into 9.1 into 10 to the power minus 31 into 0.015 upon 1.6 into 10 to the power minus 19 into 2 into 10 to the power 4 is equal to 2.92 into 10 to the power minus 9 second. Therefore t is equal to 2.92 nanosecond. From equation 1, time taken by proton to fall through a distance d parallel to electric field. Therefore Tp is equal to under root 2 mpd upon ee is equal to under root 2 into 1.67 into 10 to the power minus 27 into 0.015 upon 1.6 into 10 to the power minus 19 into 2 into 10 to the power 4 is equal to 1.251 into 10 to the power minus 7 second is equal to 0.13 into 10 to the power minus 6 second. Therefore Tp is equal to 0.13 microsecond. Equation 3. Therefore Tp is equal to 0.13 microsecond. From equation 2 and 3, Tp greater than Te. Here T proportional to root m and Mp greater than Me. The electric field components in figure are Ex is equal to alpha x raised to 1 half, comma Ey is equal to Ez is equal to 0, in which alpha is equal to 800 Newton per Coulomb meter raised to 1 half. Calculate A, the flux through the cube, and B, the charge within the cube. Assume that A is equal to 0.1 meter, epsilon 0 is equal to 8.854 into 10 to the power minus 12 Coulomb square per Newton into meter square. You can see in figure. The cube is one face is kept on x-axis at a distance of the left face is small a, and right face as the distance from the origin, that is 2a. Unit vector on left hand side NL unit vector and right hand side NR. This cube has each side small a. Face 1 left surface phi 1 is equal to vector E into vector delta S is equal to E into delta S cos 180 is equal to E delta S in bracket minus 1 is equal to minus E delta S. Delta S is equal to A square. Therefore phi is equal to minus in bracket alpha x raised to 1 half bracket over into delta S. X is equal to A is equal to alpha in bracket A raised to 1 half A square is equal to, therefore phi 1 is equal to alpha into A raised to 3 by 2 plus phi 2. Therefore phi 2 is equal to flux linked with right surface phase 2, phi is equal to 0 phi 2 is equal to vector E dot vector delta S is equal to E into delta S cos 0 is equal to E into delta S into 1 is equal to E into delta S is equal to bracket alpha into x raised to 1 half bracket over a square x is equal to 2a, keeping this value, is equal to alpha into bracket 2a raised to 1 half a square is equal to alpha into 2 raised to 1 half a raised to 1 half a square is equal to alpha root 2 a raised to 1 half a square. Pi is equal to phi 1 plus phi 2 is equal to alpha root 2 a raised to 1 half a square minus alpha a raised to 1 half into a square alpha a raised to 1 half a square in bracket root 2 minus 1 bracket over is equal to 800 in bracket 0.1 raised to 1 half into 0.1 whole square in bracket 1.41 minus 1 bracket over is equal to 8 in bracket under root 0.1 bracket over next bracket 1.41 minus 1 bracket over is equal to 1.048 Newton per coulomb meter square. Here phi comes out to be opposite, which indicate that this plus come out of a given cube. Now if net charge enclosed by given cube is cube, small q, then according to Gauss theorem phi is equal to q upon epsilon 0, therefore q is equal to phi into epsilon 0 is equal to in bracket 1.048 bracket over next bracket 8.85 into 10 power minus 12 bracket over, therefore q is equal to 9.2748 into 10 power minus 12 coulomb is equal to 9.3 into 10 power minus 12 coulomb. An early model for an atom considered it to have a positive charge point nucleus of charge Ze surrounded by a uniform density of negative charge up to a radius capital R. The atom as a whole is neutral. For this model, what is the electric field at a distance small r from the nucleus? Question mark. You can see in figure also the dotted line shows Gaussian surface 1 and 2, nucleus and atom. Here the nucleus of atom of an element with atomic numbers capital Z has total positive charge plus Ze, where plus E is the charge of one proton surrounding to this central positive point charge. Uniform volume distribution of equal negative charge was considered up to radius capital R as per the early model of neutral atom. If volume charge density of this negative charge is rho, then rho is equal to total negative charge in an atom upon volume of the spherical atom. Rho is equal to total negative charge in an atom upon volume of spherical atom. Rho is equal to q upon v. Therefore rho is equal to minus Ze upon 4 by 3 pi r cube is equal to minus 3 Ze upon 4 pi r cube. Equation 1. Now let us find out the electric field for following three cases. First, for Ri less than capital R inside the atom, consider spherical Gaussian surface with a radius Ri and surface area 4 pi Ri square. Magnitude of the electric field at any point on this surface is same because of the spherical symmetry. Let it be Ei. Here net charge enclosed by above Gaussian surface is small q is equal to capital Ze plus 4 by 3 pi Ri cube. Rho is equal to capital Ze plus 4 by 3 pi Ri cube in bracket minus 3 capital Z small e upon 4 pi capital R cube bracket over. From equation 1, small q is equal to capital Z small e in bracket 1 minus Ri cube upon capital R cube bracket over. Equation 2, therefore q is equal to capital G small e bracket 1 minus small Ri cube upon capital R cube bracket over. Equation 2, Applying Gaussian theorem for considered Gaussian surface, integration vector Ei dot vector ds is equal to q upon epsilon 0. Therefore, integration Ei ds cos 0 is equal to capital Z small e upon epsilon 0 in bracket 1 minus small ri cube upon capital R cube bracket over. Here vector Ei parallel to vector ds. Therefore, Ei integration ds is equal to Z small e upon epsilon 0 in bracket 1 minus ri cube upon capital R cube bracket over. Ei is constant. Ei in bracket 4 pi ri square bracket over is equal to capital Z small e upon epsilon 0 in bracket 1 minus ri cube upon capital R cube bracket over. Therefore, Ei is equal to capital Z e upon 4 pi epsilon 0 in bracket 1 upon ri square minus ri upon capital R cube bracket over. Equation number 3. Above electric field is directed radially outward. Above electric field is directed radially outward. Second, for small r 0 greater than capital R outside the atom, consider a spherical Gaussian surface with radius small r0 and surface area 4 pi r0 square. Magnitude of the electric field at any point on this surface is same because of the spherical symmetry. Let it be E0. Here net charge enclosed by above Gaussian surface is small q is equal to capital Z E plus in bracket minus capital Z E bracket over, both are cancelled, is equal to 0. Now applying the Gauss theorem to above Gaussian surface, integration vector E0 dot vector ds is equal to q upon epsilon 0. E0 is equal to 0, therefore q0 is equal to 0. Equation 4. Third, on the surface of atom in bracket small r is equal to capital R. If we consider spherical Gaussian surface with radius small r is equal to capital R, then the charge enclosed by it is also small q is equal to capital Z small e plus in bracket capital Z small e bracket is equal to 0, and so electric field on the surface of the atom is Es is equal to 0. From equation 3 also we get the electric field on the surface of the atom. Es is equal to capital Z E upon 4 pi epsilon 0 in bracket 1 upon r square minus capital R upon r cube bracket over. For small r is equal to capital R is equal to Z E upon 4 pi epsilon 0 in bracket 1 upon r square minus 1 upon r square bracket over. Therefore, Es is equal to 0. Conclusion: at a distance Ri less than capital R from the center of the atom, electric field Ei is equal to Ze upon 4 pi epsilon 0 in bracket 1 upon Ri square minus Ri upon capital R cube bracket over, radially outward. Second, at distance small r greater than or equal to capital R from the center of the atom, electric field is E0 is equal to Es is equal to 0.